I'm delighted to welcome Dr. Maria Rodriguez. She's from the Albert Einstein Institute in Potsdam, Golm. Is that the Potsdam Tower, the Einstein Tower? Yes. Okay, good. And also from Utah State University. And she's going to speak on Welt, the concept that changed physics. Over to you.
So thank you very much for the organizers for the invitation to come to Oxford. And already it is my first time in Oxford. I have been to the Cambridge a few times. So I'm very happy to also have seen Oxford on this trip and organizing this very, very interesting conference. And we had a wonderful morning, I think. We discussed many things about the concepts of space when those historically were developed. And also we had hanging there the course of time. And what I'm going to be talking about now is going to be the time, the moment in the history of physics and math in which these two concepts were set up in the same theory. And by that, we're going to go back 100 years. So the concept that I will try to develop is a concept that is the German word for world, that is Welt. And that concept is not something that I developed, is something that appears in the first papers where space and time were concealed in the same setup. So this is my talk, and I will try now to convince you or walk you through a few ideas. And so I will show you by introducing everyone into these ideas of space-time rather than just pure space and time. That will be one part of my talk. And then I will show you some historical developments and give you some historical context. I also want to emphasize that we always talk about Einstein and several of the other famous physicists, but many of these concepts were developed not just simply by Einstein. And there were a lot of other personalities, scientists, mathematicians, and physicists mainly, that were engaged and involved in all these theories and papers that then ended up in these wonderful papers on general relativity that Einstein wrote. So those are going to be the times in which I'm going to be focusing on or zooming in. This will be the years between 1907 and 1909, which is just between the papers of special relativity and general relativity. So something very special happened during those years, and I will give you also a bit of a gossip of what was going on behind the scenes, of what you can read of specifically on the papers that we are going to be talking about. And then what I want to emphasize finally is our current understanding of space-time. And we will have later a talk by Professor Barrow. He will develop that further. But I just want to leave a feeling that all these developments are currently being used and evaluated. And we will then open the discussion of whether this is the right thing to do or not later on. Okay, so although I'm not going to use this same structure, this is what I want you to kind of take home if you want. So we have talked this morning mostly about the right-hand side, the understanding in the history and developments in science and physics about space. And for mathematics, that is called Euclidean space. And there are many reasons of why we call that in this way. But I kind of symbolize that existence of space, of the three dimensions that we sense. And my kids do have a very good feeling of up and down and forth and backwards. And that is in this coordinates x, y, and z there that is on your left-hand side. So we do have space on one side. On the other hand, we do have time. And at the beginning of 1907, the use of space and time in the theories was completely separate. Maybe it was a bit earlier where this idea started to begin to be more mixed together and were trying to be reconciled into one. But we had Euclidean space and time was a separate line, and no one wanted to touch that. Specifically, I'm not sure about so much about the philosophy. So I'm a researcher doing black hole physics, so please do understand that I don't have that philosophy background so much. But the mathematicians were very concerned about the idea of mixing the concepts of space and time. But the geometry, the Euclidean geometry, our idea of space was no longer adequate. And for that, Minkowski, who was perhaps the person that captured that in a few papers, not because he just developed it, he captured those specifically and wrote the papers, wrote ideas, and specifically when we talk about science, we do want to see the math of it. He wrote the papers in a mathematical way in which we could really make sense of these ideas of having a space-time that he called Welt, instead of recognizing as some other words that at that time Einstein was using. So essentially, he deleted the idea of Euclidean time as being a unique concept, and he brought together these two ideas of having now a space-time. And this was something that was or is currently recognized as a Minkowski space, and we will see what his legacy is, but we do recognize that his achievement in trying and succeeding putting space-time at the same footing. So this is what my talk is about. And these are some of the questions that when I was preparing this talk, I was intrigued about. And I thought, well, maybe we can try together to go through them and see what this, if we can actually find answers to them. So one of the questions I get from some students is, why is it necessary to have actually a space-time instead of still keeping space on one side and time in the other? So I will give you some ideas and show you why we ended up in the history of science having to do this. And then the question of who were the main characters around these times when the theories were developed, and how did this then become so important? Okay, this ideas of being a space-time, rather space and time on a separate footing. On a separate level. So, and then the ideas of legacy and what our current ideas are, which I will not briefly mention at all. I will leave that to our next speaker. So, why was space-time necessary? So, this morning we had already some talks about the ether. And by the beginning of the 20th century, this idea that the ether was our main reference frame became clearer and clearer, and many of you may agree or not with this, but it was seen as a background that was undetectable experimentally. So what happened was, in 1905, Einstein wrote a paper which was postulating two of these concepts that was in some sense saying that mathematically having an ether or not was equivalent and could be actually set up without, so the theories, without having any reference frame as the ether. And for that, he postulated in his paper of 1905 these two postulates. One is the principle of relativity, not to be confused with general relativity that came 10 years later, okay? So the idea of relativity was that the laws by which all the physical systems undergo and change are not affected respect to which frame one is describing this. And the other concept was the principle of invariance of light when is propagated in a background. And this postulates, if you look back at the paper that was obviously written in German, but if you look at the papers, there was not too much of a mathematical context, on these papers. There were postulates simply as they're stated in here. So in these ideas and in the papers by Einstein, you could actually not deduce that there was a necessity of having a space-time rather than a space and a scale of time. It wasn't really explaining in math terms, if you want, that this was really necessary. So what happened after the 1905 paper was that Minkowski, inspired by also some other characters and very big scientists, as you know, which were Poincaré and Lorentz at the time, realized that by using this idea of a Welt, so a space-time description, that united this was enough to make these ideas that Einstein had postulated and have an equivalence between the different local times that each observer, each of you are actually a local observer of time, but your observations and my observations are exactly equivalent. And what Minkowski did was to write the mathematics that was necessary to understand that this was the case. So this was the magical part, but, and this is the part that then we will see more closely, this didn't come as easy as it sounds. Making this progress and having personalities like Einstein and Minkowski fighting for these ideas was very, very interesting to study as well. So the first paper that Minkowski wrote actually on relativity, not general relativity, was this paper in April of 1908, okay? And that paper in April of that year was very controversial. All the physicists that were doing experimental physics hated that paper. He was stating in that paper that space-time had to be united and Lorentz transformations were going to give us the equivalence between the different systems that one needed. And this was something that experimentalists really were against, and only a small community of the mathematicians were more in favor about these ideas. And so what happened was, four months later, in September of 1908, he presented a talk that was called Spacetime, Raum und Zeit in German, where he made these views more appealing to both the physicists and the mathematicians. So he stated, "The views of space-time which I wish to lay before you have sprung from a soil of experimental physics, and that's where it lies its strength." So he was trying to capture all these experimentalists that were very, very against his ideas. And henceforth, space by itself and time are doomed to fade away into mere shadows, and only kind of a union of the two will preserve an independently reality. Okay? These were his ideas, and this is how he started his presentation in September of that year. And this is when we saw, historically, that many other fields started to approach these ideas and become more friendly, if you want, to these ideas of concealing the theories as theories of space-time and not simply space. So these developments were in April and September of 1908. There was also another development which has to do with Minkowski's death. He died in January of 1909, so a few months later, after his very big presentation on space-time, he passed away in Göttingen. He was a professor there. And this changed the stories that I'm going to now tell you. So we all like TV and gossip, and these are the phases of this novel. So we do have on the on your left-hand side, Minkowski's face. Okay, this is the person that, and I tried to get pictures of them more or less by the times in which these papers were written. Okay, so this is how more or less they looked at that time. So Minkowski on the left-hand side was the person writing these papers, and there was Einstein and Laub, that I don't have a picture of Laub. Maybe there's someone that has that in the audience. So why are these people in here? Well, what happened was when Minkowski wrote his paper in April of 2008, Einstein and Laub actually wrote papers against what, perhaps not so enthusiastic about the ideas that Minkowski had developed. And what happened was that Born and Sommerfeld were very supportive of Minkowski at that time. Sommerfeld was the big face in this support because he was the editor of the Annals of Physics at that time. So he was very important in there. And Max Born was in Göttingen, and he has a very good account, and there's in his biography accounts of those years as what the role of Minkowski was and how it was his work was perceived by the different communities. So the clash between Minkowski and Einstein can be looked back even at the years in which Einstein was a student. Minkowski was his professor in math at ETH in Zurich. And Einstein was perhaps, and this is not said by me, but in several papers, historical papers, he was more a math lazy student, and he liked to do more the experimental classes. So what happened was Minkowski, which was a mathematician, thought that Einstein was a lazy student. He didn't understand that Einstein was going to become more fond of mathematics later on. And Einstein thought that his teacher was very theoretical. And these are accounts on both sides. So, and in the end, the problem here is, as you know, scientists have these very, very big egos, and they don't want to give up their names on these ideas. And the problem at stake here was eventually who was going to be recognized as the person that concealed not just the theories of relativity, but maybe these ideas of space-time, okay? So there are many papers that you will read about, and the biography by Max Born as well, that will take you through specifically those 2 years in which these ideas by these people had been developed, and there were fights in the background that were never written specifically on these papers. Laub here, that I don't have a picture, is the person that wrote a few papers after Minkowski's papers jointly with Einstein, and this is why he was there. And so in this paper, and there's a typo here, I meant Laub and not Laue, from Laue, is that they acknowledged that Minkowski, so in a recent published study by Mr. Minkowski, they presented the fundamental equations for electromagnetism, but what they say is that what they're now analyzing is in agreement with Minkowski, but not emphasizing that his math approach was actually the correct way to go. So these are the first examples after Minkowski's studies in which Einstein starts to develop a more theoretical and mathematical approach, and starts to learn all the tools necessary to develop later on general relativity. So some historical notes that I found interesting that maybe are also, so I also just mentioned this, that Hermann Minkowski was Einstein's former math professor. And, but nevertheless, Minkowski, although he was, sharing a lot of his thoughts about Einstein being not so a math student, but rather a physicist, he never took, and at least this is what's written in the papers, made a priority to claim that, his views of space-time were done by him. He actually acknowledged that Einstein was the one that had done the great discoveries. Okay, and this was in a very short time because the papers by Einstein were in 1905, and he passed away in beginning of 1909. So this was very close to each other. Something interesting is also that the papers by Minkowski, when you look at when they were published in 1915. So how can that be? Well, if you have powerful friends and they're the editors of the Analysis of Physics, they can have that power. And actually, after the death of Minkowski, there were a few physicists and mathematicians that were in charge in trying to publish anything that was left in Minkowski's office with Minkowski's name. There are a few papers, and in particular, there are a few papers that were also rewritten. And they were rewritten, so if you look now back to the papers, and one has to always remember that it is very different what we researchers think and then what the editors do with our papers and titles. Okay, so, and this happened. So if you look at the original manuscript by Minkowski, there's a big difference between that and what Sommerfeld himself changed and published on Minkowski's name 6 years after his death. Okay. So that is something interesting that happened. Sommerfeld was this huge professor with a lot of power in Germany at that time, and had a lot of people working with him. And yes, so anyways. So those are the historical notes. So what I did here was to give you a brief time scale or timeline about this, and I wanted to fit in so that you have an idea with this 10 years at the beginning of the century, how we changed radically from space and time to 15 years later talking about general relativity. It was crazy times for space-time at those times, and a lot of things happened between there. And I'm stressing here only Minkowski and Einstein because I was asked to do so. But as you know, there was a role by Hilbert, there was a role by Poincaré, and there was also a big role developed of the developments done by Lorentz. So in here, I just wanted to sketch this timeline of what happened. So what is Minkowski's legacy? And how did all this fit? What's written in his papers that is not written in Einstein's that makes us think that Minkowski's contribution to these ideas were really very important? So, and I took this from some papers here that are the references in red, and I have a few references more. I was a bit sloppy there of not having the references all the time. So Minkowski considered the world, the Welt, the space-time, in a very single form. And so he expressed that this quantity, the square of each of these coordinates that now include time, and which is multiplied by the velocity of light squared so that we have the same units, and the expressions of x, y, and z, our three coordinates in space squared, had to be something, some constant, and that was an invariant. And in physics, anything that is invariant, we go crazy for it. And so what happened was that gave us the idea that any system of reference, now prime all your coordinates and time, and this is written in Minkowski's papers literally, there on the right-hand side, you can re-express this equation in the same way, now with all primed, and you have to have the same number in here. So that is what related one coordinate system, yours, which are the primes, and mine's, which are unprimed, and in which we put some value squared, and we have to observe the same number. This means that every local observer has to measure this same number, independently of which system of reference or time scales you're using. And this could only be done not just with space, as with Euclidean space, but also with time. So there was a different measure of what time was for me and what time is for you, which is the time primed, and I'm the time without the primes, but there was a way to change that system in a way that we have finally the same measurement, and agree on this as well. So Minkowski introduced words that we currently use in science and teach our physics students, which are these ideas of Weltpunkt, world point, and Weltlinien, so world lines that we have. This was the first time that they were introduced. He was the first that wrote expressions like this for the invariance in relativity. And he also started developing ideas that explained the ideas of contractions and expansions of space and time. Although he didn't and did not do this very precisely, there were some ideas in his papers. So this then was referenced by Minkowski literally in his papers as Welt, which is the name that I tried to name my talk. So his contributions were very strong, and one way to measure that, I'm a physicist, I need some data. So how do we measure that? Well, what I thought was to stress that there was some ideas of how many publications there were at the time. And this was kind of interesting. In comparison to today that we have the electronic version of the publications, it was interesting to understand how many publications there were per year. I would have loved to be at that time. So there were in 1908, there were 32 papers on relativity, the whole year. 3 years later, or 2 years later, after these developments of the more mathematical papers and also Einstein's further papers on relativity, they were tripled the number of papers. And these are papers on relativity and not in general in physics, okay? So in 2 years, the interest started to increase. So the references are here. And what I wanted to mention, and maybe I have some experts in the audience, is the following. I'm currently a physicist working at the Max Planck Institute, and I spend half of my time also in Utah State University. But in Berlin, I found that Minkowski was buried. And so I'm very intrigued because Minkowski passed away in Göttingen. And in Göttingen, in the cemetery, there are very, very famous people and physicists at that time that are buried. So I wondered what happened between, and yes, you know, there were a few wars in between, which, you know, makes him completely displaced in the context of that time. Why is he not buried in the cemeteries in Göttingen with Hilbert and all the other physicists? So I tried to trace that and maybe understand what happened during the times later on. But if someone has a reference or someone I could ask, I would be happy to do so. I leave you with Professor Barrow and saying that for me, not having space-time would be or would make my research almost impossible in trying to study black holes. And I hope you have questions for me. So thank you.
So, I have plenty of time for questions. Yes, there's one up there.
Dr. Maria, if I'm not wrong, thank you very much indeed for the enlightening talk. Bear with me while I pose this question to you. Firstly, remembering Einstein, I'll say, Ich bin heute gut drauf. I don't know if I've said that right, but anyways. Going back to your very first slide, you mentioned how Euclidean geometry was replaced by the additional dimension which Minkowski added. And then towards the end, you talked about the equations that he developed in the slide where you mentioned the legacy of how X, Y, Z, and you've got E and T and the different consonants. Not going into the philosophy or the metaphysics, but mathematically and in terms of physics, we've discussed Newtonian space this morning and how the Newtonian view of an absolute void of space was refuted by Einstein and the thinkers that you mentioned here. So traditionally, matter was seen as something that persisted in time and moved in space, and the Newtonian view was refuted. So my question simply is, if we take time to be a dimension effectively, does that mean that the future exists as an open possibility rather than something, is it fixed or is it an open possibility? That's the gist of my question, so if you can shed some light on that. Thank you.
So thank you for your question, because it actually gave me an idea that you're correctly in the time in which this was developed. What they were talking about were actually in the context of massless things. They were talking about electromechanics here, or dynamics. What happens with mass will be the role that comes next, okay? So what they did at this point in time was just to unite space and time, and then the developments of how mass, was put into place with these new things is probably what we will hear in our next talk. So it's not that I cannot answer your question, but I think this is where we currently are, and there will be a huge effect to that, specifically. So thank you for the question. Yes.
Hi, thanks for a great talk.
Okay.
Nice to hear about Minkowski instead of Einstein all the time. Great. Question, a very quick question, and it's a mathematical question of the physics, and because I don't understand the derivation of the c squared t squared minus x squared, where it actually derived from, but the minus sign creeps in. Is that something to do with the square root minus 1? Something like that?
So the sign difference between the time and the space.
Yeah, absolutely,
right,
yeah.
Exactly. So what happened is, when we call something Euclidean, a space, that has a signature that it can be either positive or negative, and in this papers in particular had a signature with a negative sign. The time would have the contrary sign, and that is and was required by the theories of Lorentz. So a Lorentzian spacetime will have a signature and sign that will be different between the opposite of the space than the time. Right. So I would have to take 5 more minutes and doing a bit more of math than just giving you that to show you how you end up with that equation. Well, that's also possible. Yes, sure.
Okay. Thank you very much for a really interesting talk. I was taken by your comment that there was some resistance from experimentalists. Mm-hmm. And of course, if we look back, the invariance of electromagnetism and Maxwell's equations under Lorentz transforms was probably known almost from the time of Maxwell through Lorentz, Poincaré, and so on, and probably reasonably well established by 1900. So I was wondering what you thought the barriers were to the experimentalists taking up Einstein's work.
So let me put you back in the mindset also of the beginning of the century. Experimental physics was the physics, okay? Math and theoretical physics were for just, other people. So there was a very small community, and experimental physics was the cool thing to do. And it was such that only the brightest students wanted to go to experimental physics. This is why Einstein was really interested more in the experiments than the other things. So it was puzzling at the time, because that were the first shifts again, in which theory was trying to tell the experimentalists something, and there was a lot of an objection in doing this. In particular, there are some references to Wien and some other experimentalists at the time that were literally sharing letters among each other after the conference, because the conference that Ramsite in September of 1908 was presented to the physics community, not just the theoretical community, but at wide, is German physicist community with experimentalists. So they were, and there are letters that show exactly that they were not very happy with these ideas. Why this resistance, it was perhaps that it always takes some time, and in particular there were the math necessary to catch up with the experiments wasn't even developed. There was. So, but I don't really know exactly why there was so much resistance.
Following on from our friend's comments here, was Minkowski familiar with Hamilton's Quaternions?
I don't. So I haven't found any information about that. So I can't answer that question. How much informed were all about all the other works? I don't know about that. Mm-hmm.
Yes, I'm sorry. I'd like to make a remark about your Minkowski puzzle. I think, do you know, there are two different versions of relativity theory. The first relativity theory was developed Henri Poincaré many years before Albert Einstein. Lorentz invariantness, all mathematicians know, was developed namely Henri Poincaré, not Lorentz. The first reference by Albert Einstein to relativity theory developed by Henri Poincaré was made only in 1926. The first reference. Maybe in some sense, I'm not sure, but maybe in some sense this kind of politique may be connected with your Minkowski puzzle, because Minkowski really connected with Henri Poincaré development. Mm-hmm. I'm sorry.
No, and another fact here is also there were big fights between Hilbert and Einstein at that time. And Minkowski was very good friends, or more friends with Poincaré, and very good friends with Hilbert because they went together to school. And so there were all these things, and it's completely true that we tend to not acknowledge the work of Poincaré, but as I said, I focused more on the developments of what was happening in Germany rather than that. But Poincaré was part of some discussions that happened between 1905 and 1907, in which Minkowski invited Poincaré and Hilbert and Max Born in discussions where they requested from Einstein a copy of his paper of 1905, and they really studied the paper, and that's where all the discussions came about. Einstein wasn't invited to this set of lectures or studies, and he found the results in these papers then in 1908. So, yeah.
I think it's true that in the 1905 paper, Einstein had no references.
No.
He obviously didn't reference Poincaré.
No.
He even denied that he knew the null result of the Michelson and Morley experiment.
Mm-hmm.
Yes.
There's a comment about Maxwell and electromagnetism.
Mm-hmm.
I think what happened there was a sort of failure of mathematicians. You know, after Newton, there were people like Euler who developed the mathematical detailed picture of the consequences of Newtonian mechanics. But Maxwell, who was rather retiring, didn't push his theories dramatically, and he died at a very young age, in his late 40s. It just wasn't developed in the way that it should have been by mathematicians. Ebenezer Cunningham was the first person who showed that Maxwell's theory was invariant under Lorentz transformations. But he sort of really went on to become an administrator in Cambridge after becoming senior wrangler. Dirac wanted to be supervised by Cunningham, but Cunningham was off on sabbatical, and he said he never really got back to doing research because he was a rather good administrator. So in this period, there was a failure to develop the mathematical language and environment of Maxwell's theory. Probably if Maxwell had lived, he would have done it.
Yes, this one.
Thank you very much. I think this relationship between theory or mathematics and the experimentalist is quite an interesting one. Because I think in quantum mechanics at the 10th century, you know, you can see again, experiments were leading, and then there was some intuition developed from the theory division of the theoretical physicists. I'm just wondering, with Minkowski, because that's another interesting phase change, what were the experimental observables that he was looking at, such that he could then go on to make this leap, or this quantum leap, into sort of unifying, or thinking about unifying space and time and creating this invariant quantity?
So the most interesting point here was the discussion about capturing in some math equations these ideas that the speed of light could be a threshold from which we could not advance any further. And there, I didn't show them here in my slides, but also he has the phase diagrams of these cones that you can write now your space-time as, in which you cannot, as an observer, go beyond the speed of light, and either you're doomed to be within that cone that you have. So I would say it's always the speed of light, perhaps what he was capturing there in his equations as the experimental test. But he was a mathematician, right? So he wasn't trying to really convince the experimentalists. He was perhaps framing his paper of April in that conference in September in a more friendly way to see if he could capture them in some sense. And let me say, I'm a theoretical physicist, and this resistance and fights still exist between experimental and theoretical physics. So, yes.
Hi, thanks for a great lecture. We had a lot of fascinating insights from history. So I would like to ask about today. There was a very dramatic title a few months ago at the New Scientist magazine saying, "Time and space, one has to go, but which?" So my question is, in your view, is space-time as a concept under pressure in current theoretical research? Certainly people like Lee Smolin and Carlo Rovelli have been very vocal and published sort of great popular and scientific material on the notion of time and space.
So the ideas of we still are discussing those things, because there was some reference previously before of whether there exists a theory of quantum gravity, correct? So there are two great trends, which is string theory and loop quantum gravity currently, that discuss these things. And when we discuss those theories and who's wrong and right, we are always discussing backwards the essence of that space and time. Saying in this also, take in notice that general relativity or all these theories don't put a cutoff on the number of dimensions that we have, of space dimensions. And so there's still yet, an ongoing discussion on this. And sometimes, though, I must say, the journalists take a bit, it's more than the editors. They take and stretch our words in, but there is a conversation. There's always this idea, but I don't think it's so much about detaching space and time, because we have now evidence with gravitational waves, with these ideas of finding black holes in our own Milky Way. In the center of a Milky Way, you will see at the end of this year possibly more evidence that we are plugged with black holes. And so it will be very hard to, in some sense, get rid of general relativity and these ideas of having a space-time. Now at the quantum level, quantum gravity, there could be still the discussion of trying to detach them in some way. But for general relativity, I think we need to conceal our ideas and, be fine with these ideas of having them together.
You mentioned black holes and space-time. Without space-time, it would be almost impossible to do your work on black holes. Could you elaborate? Because from what I've read on black holes, it's described as literal swirling space-time kind of.
Right, so there's one concept that makes you think, if you believe in general relativity, which apparently we do have, given all the information and the experimental data, that makes a huge difference between what we call a black hole and the rest of that. And that's the surface that describes a black hole and anything, matter that is out there. The only difference that a black hole has in comparison with the rest is its event horizon. And event horizon has, as the word has, an idea and a concept of time as well in there. So in this sense, I think that my work could be mostly irrelevant if I don't believe in that there's a way to have at the same footing time and space, because it would be very hard without doing this to describe what a black hole really is and make this difference between any other object and a black hole.
Well, in that case, I'm going to abuse my position as chair and ask a question myself, if I may. And this is really an unfair question, it's not a history question. It's clear that Minkowski was able to explain the transformations of Lorentz and Poincaré. Mm-hmm. Would we have got there without Einstein?
I think we need all of them. It would have been impossible to develop all those theories, and people in the background like Max Born that did not write. I mean, he ended up being recognized for different things, but Max Born was invited by Minkowski, and all those years was in the background of Minkowski's developments. We are social creatures, and I don't think I could have written my papers without even discussions and, you know, how you build an idea. So I think you would have needed all of them in order to develop all these theories. And in particular, Einstein understood later on, I think, this math, this necessity of having this math description. So
let's thank Dr. Rodriguez.